Hello, good evening. Am I audible? So, very good evening to one and all present over here. So, I'm very much thankful to Bharti for giving me an opportunity to discuss about very important topic from the syllabus of NET and SET of the physics. So, also I'm thankful to Mr. Rajiv Gandhi sir from Bharti for organizing sessions very frequently. So thank you, and thank you all dear students for your huge response and queries through mobile as well as through the YouTube. So friends, as we are discussing about the electronics and electronics, when we are discussing about electronics, we know so there are various components which plays a vital role in electronics, and without that we cannot imagine the electronics. And like that, in earlier or in previous lecture, we have discussed the role of PN junction diode, how it works, what are the characteristics of the PN junction diode, as well as what are the different applications of diode. So in line with that, another important PN junction device is the bipolar junction transistor, and we call it as a BJT. So as we know, when we discuss about transistor, so the name transistor comes from trans plus resistor. So here simply the meaning of trans plus resistor means so the transfer of resistance from the like a low resistance region to the high resistance region, and that is why name is here like a transfer of resistor. So when we are discussing about transistor, then we know we are having two major category of the transistor. One is the unipolar junction transistor, another one is the bipolar junction transistor. So here we are going to focus on bipolar junction transistor in today's session. So in case of bipolar junction transistor, we know there are two category or the two types of the transistor. One is the NPN transistor, another one is the PNP transistor. So accordingly, we have two different types of the bipolar junction transistor. And again, we know if we are having transistor, then it has a three different or the three terminals. And then according to the application or according to the biasing, we are having different application of the transistors. And then conventionally, as we know, we required minimum to input and minimum to output. That is why what we do, we can have the common emitter biasing or the mode, we call it as a mode. Common emitter, then the common base or the common collector mode. And accordingly, we can have the different kinds of the input circuitry as well as the output circuitry. So in that way, we are discussing about the bipolar junction transistor. We will see one by one. So whenever whatever electronics, as we know, around 1950s, the transistor is invented, and since that time, we know how there is a transformation in terms of electronic circuitry. Earlier to that, earlier to transistor, we know there were some like a tetrode or the we call it a triodes, pentodes, and that is what we call the vacuum tube devices. And if we see the size of vacuum tube devices, and then the heat dissipated by these kind of the devices, as well as the voltage requirement for that devices, this all where we can consider as inadequacies of these all kinds of the devices, and these all inadequacies were overcome by the simple transistor. And that is why nowadays, as we know, we can integrate millions of transistors in a VLSI circuits, and accordingly we are having the LSI, VLSI, VVLSI and all. So it's only because of these all things are possible only because of the invention of transistor. And like that, like the transistor, again we know we are having now the nano transistor also. You may be knowing IBM has filed the patent about the nano transistor also. And again, according to that, like according to is that again now we just I have discussed the millions of transistors can be integrated into any of the ICs. Then again, if we go for the nano transistor, then again the number will be more. And if number will be more, then the function or the desired function we can achieve with the help of the transistors. So if we see the basic electronic system nowadays, it's semiconductor devices. Whatever system we see, so it's all made up of the semiconductor devices. And again, when we talk about semiconductor devices, then I told you initially, it begins from the diode, then we move to the transistor. And then again, after that, the LEDs, and again, so many and so forth. There are different electronic devices. So the famous and commonly used of these devices is the bipolar junction transistor. As I have discussed, initially, why bipolar junction transistor is of most important, because the purpose or the process of amplification can be takes place only with the help of the transistor. And for the process of amplification, transistor plays a very vital role. And again, not only for the process of amplification, but for switching and other application also, transistor can plays a very vital role. And that is why transistor is can be considered as a versatile device in terms of the electronic system. So again, it can be used as amplifier and logic switches. So as I have discussed, like logic switches. So in the process of switching, if you want to switching from one circuitry to another circuitry, then transistor can be used for that purpose. And again, we know, as I have mentioned, there is a common emitter, common base, and common collector. So that these biases or these kind of the circuitries we have to use as per the applications or as per the requirement. And then again, now again, as everybody knows, because how BJT is there, but again, so if we want to understand more about the transistor, then we need to revise also. So simply everybody knows this BJT consists of three terminals having the collector, base, and emitter. And again, the name of these terminals are also given. Given out the name like emitter. Emitter emits the electron or the charge carriers, maybe the holes. Then base just passes the charge carrier from emitter to collector. And the function of collector is that collector can collect the charge carriers, which is just pass from the base and emitted from the emitter. And that is why the name is here emitter, base, and the collector. And then again, we are having two types of the bipolar junction transistor. One is PNP and NPN. So as I have mentioned earlier, we are having these two types of the transistor. Now, again, just a briefing. So this is a three-layer semiconductor device consisting of two N and one P layer of the material we called as the NPN, or the 2P and one N layer of the material is called as the PNP transistor. Then the term bipolar reflects the fact that holes and electrons participate in the injection process into the oppositely polarized material. Why it is so? Why they are participated like that? And then how the depletion region can be formed, because we are doing the biasing like that. So simply you can see, if we want to go for normal operation, then what we do, emitter to base junction is forward bias, whereas base to collector junction is reverse bias, which means that what will happen, because of forward bias, the charges will be move on or just trying to pass on. But whereas the base to collector is reverse bias, it will stop or it will just resist. And again, because of that, there is a formation of depletion region where there is a recombination of electrons and holes will be takes place. So this is again the beautiful concept we will discuss in coming slides also. So a single PN junction has two different types of the biases. One is the forward bias, another one is the reverse bias. So as I have mentioned, and again, thus a two PN junction devices has four type of the biases. We can see here how these four type of the biases can be possible. So if we look for these four types of biases, then you can see base is located at the middle and more thin from the level of collector and emitter. So this is what about the transistor. So let me just go back. Now, thus a two PN junction devices has two types of the biases. What does it mean? So the as I have just shared here, emitter to for normal operation, I'm using one word. For normal operation, emitter to base junction is forward bias, and then the base to collector junction is reverse bias. But for typical or like a non-conventional operations, what can be done? We can have reverse of it. So emitter to base junction is reverse bias and base to collector junction is forward bias. Both are forward bias and both are reverse bias also. So in that way, we can think and we can have the different aspects or the different biasing of the transistors, and accordingly we can have the different applications. Now let us see about the construction of the transistor as well as the symbol of the transistor. Very simple is here. So base is located at the middle and more thin from the level of collector and emitter. So as everybody knows, the collector is larger in size. Here we can see emitter is moderate in size and base is thinner in size. So simply, and again, if we see the doping concentration, so emitter is heavily doped, collector is moderately doped, and base is lightly doped. Because base has a role to pass the charge carrier from emitter to collector. And the emitter and the collector, you can see terminals are made up of the same type of semiconductor material, while the base of the other type of material. So here simply we can see here base is N-type material, whereas collector and emitter is of P-type material. Here also base is P-type material, your collector and emitter is of N-type material. So in that way, we can have this. Then transistor currents. Now, how current will be passes from the circuit? So simply you can see here the current passes from collector, we called as a collector current. Current passes from the emitter, we called as the emitter current. Current passes from the base, as everybody knows, we called as a base current. Now, so the arrow is always drawn on the emitter, as we know, whenever we are drawing the symbol, and even though after completion of MSc, after completion of like a doctorate or the PhD, also I have seen many times how people are just trying to draw the like a simply trying to draw the symbol. So they are doing this like that. You may be surprised, or sometimes just if you may be doing so, please make it correct. They are drawing symbol like that. So arrow is right. Yeah, either they can give here or sometimes they can give here also wherever. But you can see here. What does it means? This is the so all terminals will get what will get about all the terminals. मतलब यहाँ पे क्या होने वाला है? तो so circuit will get break. सब तो एक ही हो जाएगा. It will be working like conductor. How it will be working like that ना? Means how do we get the action? और the desired action, तो ये तो short circuit हो जाएगा. So friends, don't do this. So this is not the good way to do in case of the symbol of the transistor. That is why just I am trying to explain the basic here. The arrow is always drawn on the emitter, that everybody knows. The arrow always point towards the end. N type means here you can see if it is NPN, then arrow is pointed out. So this is the NPN transistor. As we know, arrow is pointed out from the base. And if it is PNP, then arrow is pointed towards the base. So in that way, you must have to remember these two. And the arrow indicates the direction of emitter current. This will indicate the direction of emitter current flowing to the emitter. And that is what the indication of the arrow. Here you can see the emitter current, how it is passes. We can see here also you can see the emitter current is moving towards the base. So in that way, we must remember we are not going to make a mistake while drawing the symbol. So you can see simply this is the correct symbol you can see, and whether you can make the round or not, that is okay, that is not required, but you have to draw the correct symbol like that. Whatever it may be, PNP or the NPN, मैं यहाँ पे just दिखा रहा हूँ. और round is not compulsory. कि आप अगर उसको circle करना है या नहीं करना है, so that is not compulsory. So it's your choice. So this is the right symbol. So please make it and just remember forever in your life as a physicist. Now, let us see by imagining. Yeah, this is not true. Again, I am telling you, just this is the analogy. So I am just telling you, I am quoting one example of my student of the undergraduate. So as in some of the book, it was written ki by imagining the analogy of diode transistor can be constructed like two diodes that connected together. And it can be concluded that the work of transistor is based on the work of diode. So this is what the analogy. But in reality, it is not possible. So my one of the undergraduate student came to me and he was asking, sir, can I do it? Can we verify it? So I just asked them, okay, let's go ahead. So I have given diodes, I have given transistor. I have given breadboard, connecting wire, and the remaining ammeter, voltmeter, and like a power supply. And then I asked him to construct the circuit. And then he made it circuit like that. Here you can see this is the diode, this is the diode. It is connected back to back. Then he said, suppose this is the PN. This is P, this is N, this is N, this is P. Like that. Now what is happening here? Here you can see N is combining together. And once you combine the N region of both the diode, then what will happen here? Here your size of base will be increased. And according to the theory of transistor, how base should be? Base must be thin. And that is why it is not possible to get the transistor if we connect two diodes together. Always you remember. That is what the simple thing. Only by analogy we can say that. If we connect two diodes back to back, then we can get the transistor. Here also you can see. We can see this region, this one. And again you can say like that. This is the P region. So like a P we can combine and we can have the NPN transistor, but it is not possible at all. It is not possible at all. So always you remember this is not possible and we don't want to do it. So just by analogy, you can remember that if we connect two diodes, then there is a formation of transistor. So as you may become the teacher, so don't try to give because student may remember if we connect, and then they used to write in examination also. If we connect two diodes back to back, then there is a formation of transistor. I have seen in some book. So this kind of mistake should not be there in any of the book also. That is why just I tried to keep this particular slide here. Now I'm coming to this. Any question? So in between that, if any question, so please. I'm just looking to the YouTube. How many questions are there? Okay, let us move ahead. So, like most of the basic I have tried to cover. Now, let us discuss like further. If we see this like a transistor or the transistor operation, then simply the basic operation will describe using the PNP transistor. So here we have taken the PNP transistor. The operation of the PNP transistor is exactly the same if the role played by the electron and hole are interchanged. So just simply we can change the role played by the hole and electron. So one PN junction of a transistor is reverse bias, whereas the other is forward bias. And simply here you can see how the recombination will be takes place. So this is what you can see the deflection region where electrons and like here you can see negative charges and the positive charge means electrons and holes are getting recombined. So the here holes are the majority charges. So now forward bias junction of a PNP transistor, and here you can see reverse bias junction of a PNP transistor, where what will happen? Here you can see the recombination region, how recombination region will be formed, and how there is a recombination of the majority and minority charges will be takes place. Now here you can see the entire picture, and that is most important, and that is happening always. So that is what expected to connect the transistor like that. As I have mentioned, emitter to base junction is forward bias and base to collector junction is reverse bias. So you can see by using two batteries VEE and VCC, we have connected it by using two power supplies or the two batteries. And again, with the help of that, we have given the power. So once we apply the power, then you can see how the charge carriers will be moving. So both biasing potentials have been applied to a PNP transistor and resulting majority and minority charge carrier forward flows indicated. You can see here how they are flowing. Then majority carriers holes will diffuse across the forward bias PN junction into the N-type material. And here diffusion is takes place. And that again plays a very vital role. A very small number of carriers positive will through N-type material to the base terminal, resulting IB is the current flowing through base, is typically in order of microamperes. Always why and the large number here, just again I want to write, if we see the current passing through transistor, there is a beautiful equation of the current. So like if you see the current passing through emitter, like why it is in microampere, here you can see the word microampere is written and it's most important. And why it is so, you can see if the current passing through emitter is 100%, then it will be always equal to IB. This is equal to IB plus IC. This is equal to IB plus IC. What does it means? You only 1 to 5% current. Here you can see only 1 to 5% current will drop to this IB, and that is why. So here simply you can see the current measured in or the flowing through base is in microampere, and this must be in milliampere. This must be in milliampere, and this equation can be satisfied with that. So it's a very much important equation of the transistor. The large number of majority carriers will diffuse across the reverse bias junction into the N-type material and into the P-type material connected to the collector terminal. So here you can see how diffusion will be takes place. Very simple and beautiful diagram is shown over here. So we can see that. Then majority carriers can cross the reverse bias junction because the injected majority carriers will appear as minority carriers in the N-type material. So they will be appear in N-type material as a injected minority carriers. And applying the again the Kirchhoff's current law to the transistor. So we know, as I have mentioned, that equation IE is equal to IC plus IB, and the comprises of two components, the majority and minority carriers. So IC is, you can see, majority, and the IC O is like a minority. So ICO minus IC, that is current with emitter terminal open, and is called a leakage current. So that current also we can get it. Now let us focus on if the configuration, as I have said, we can have three different types of the configurations. So got it till again any question? Any question? Just you can think for 2 minutes and let us answer. Any question? I am just So let us come back. So as I have mentioned, there are three different types of the configurations. One is common base configuration, then the common emitter and the common collector configurations. So common base terminology, as we know, how it derived. So simply in a very first slide, I have mentioned and I said what I said. Transistor is three terminal device and conventionally for giving input, how many terminals we required? We required two terminal. And taking the output or the for the measurement of output also, we required two terminals. And in that way, we have to make one terminal common. And so common base configurations, like common base terminology is derived from the fact that the base is common to both input and output of the configuration. Like a base is now here common for input and output configurations. So like now base is usually terminal closest to or at ground potential. So as we have mentioned how the potential should be and how we can bias the transistor. So here you can see the all current direction will refer to the conventional whole like a flow and the arrows in all electronic symbols or direction defined by this convention. And note that the applied biasing voltage sources are such as to establish the current in the direction indicated for each branch. So let us see now. If we are making base common here, so what we have done, we have made a base common like here. So once we make the base common, then we are giving current through the emitter, and then again here we are collecting here how the potential is there, and again how the direction of the current would be. So in that way, we can understand very easily if we make a common base configuration, then how the current will be flowing through it. So from where, like if we are having PNP, then here you can see the emitter current is flowing, then it is passing through the base, and again here we can get the collector current. Here also you can see base is common. So like in that way, the configurations will be. And now, once we apply the potential difference, once we increase the potential, then we can see how there is a changes, how there is a changes in a VI characteristics. And these beautiful characteristics gives us lots of information as a transistor is semiconductor device. So here you can see this particular, the first one is the input characteristics. And if we see the input characteristics, very small voltage is given here, like a 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, like that. And if we increase this voltage and if we try to measure the current, that is emitter current, then here you can see we can get the graph or the nature of the graph is like that. So this is the output voltage we are keeping constant at VCB is equal to 1 volt and the 10 volt or the 20 volt, anything we can keep it. And here from this value, we are able to calculate the cut-in voltage. And here we can see the cut-in voltage for the silicon and the cut-in voltage for the silicon, as you may be knowing, it may be about 0.7 volt. And whereas the cut-in voltage for the 0.7 volt, yeah, I'm not able to write appropriately. This is a 0.7 volt. And for the germanium, it is 0.3 volt. So this is what the cut-in voltage, and that can be calculated with the help of the input characteristics of the transistor. But again, we are more interested, or we are interested into the output characteristics of the transistor. And if we see the output characteristics of transistor, then you can see here how beautiful characteristics is here for keeping input current constant. So here you can see we have kept input current constant, and for which we have drawn these characteristics. And in these characteristics, you can see how we have increased the voltage. And here you can see the potential begin from the negative like minus 1 to like minus 1, then the 0, 5, 10, 15, 20, 25, like that. But here you can see how this characteristics is. So simply this characteristic we can extend like that. You may get some graph if we try to extend like that. Okay, so this is what for the common base, and that is why it is shown like that, whatever shown in picture. But if we go for the common emitter or the common collector, then we can get beautiful graph like that. And then here it falls into three different categories. Like here you can see this region, the region which we can see, this region is called as the active region. Here it is written. Then this region of the transistor, here you can see the blue colored which is shown here, it's called as the saturation region. This it is written is saturation region. Whereas the region below this, like that, this region, or just below to this, we can see this region can be considered as a cutoff region. And now, depending on the application of transistor, depending on the various application of the transistor can be operated in these regions. Transistor can be operated in a particular region. And that is what the importance of the different regions. And we can have the different like applications of the transistor as an amplifier, transistor as a switch, transistor can be used to avoid the thermal runaway. So there are different applications. Even though transistor can be used as a logic gates, or the in the circuitry of the logic gates. So the initial, if we see the circuitry of the logic gate, it is made up of the transistor. So to describe the behavior of common base amplifier requires a two set of characteristics. As I have mentioned, the input, we call it a driving point characteristics, output, or the collector characteristics. So this word is most important for you in view of competitive examination. Input characteristics is also called as a driving point characteristics, and the output characteristics is also called as, here we can see, the collector characteristics. So these two words are most important for like MCQ type of the questions. The output characteristics has three basic regions, and as I have mentioned here, you can see defined by the biasing arrangement, simply active region, then region where the collector current is 0 ampere, saturation region of the characteristics to the left of this, like that. This is called as a saturation one. So in that way, you must remember the different characteristics, and that will be useful. Now, in these regions, what is happening? Again, for comparison, comparatively, you must remember for your examination. So in case of the active region, here you can see if IE is increased, IC is increased. Means emitter current is increased, your collector current is also increased. So you must remember. But in case of the saturation region, like first we see the active region. So what is happening in active region? So if IE is increased, IC is also increased. Then BE, base to emitter, or the emitter to base junction is forward bias, and collector to base junction is reverse bias. So initially I told you for the normal operation, and refer to the earlier graph. So this is somewhat so IC is approximately equal to IE. So as I have mentioned already, why it is so? Because this equation IE is equal to we are having this equation. It's a very much important equation. IE is equal to IB, IB plus IC, and simply here you can see these two, this current IE current and IC current is in milliampere. As I have mentioned earlier, the base is very less, and because of that here we can see these both are equivalent. So IC not depends on VCB. Then suitable region for the transistor working as an amplifier. So you can see this is the application of the transistor when we operate in active region. So it's a peculiar application. And again, we know if we go for the transistor with different biasing like common emitter or the configuration, instead of biasing, we can say common emitter, common base and common collector. Then we can say that we are getting some parameters like alpha, beta and gamma. We call it as a current gain. And if we are using transistors in common emitter mode, then that particular parameter, like beta is, so beta is more than 100. It is in between 100 to 500. And that is why the common emitter configuration can be used or can be considered as one of the best configuration for the process of amplification. For the process of amplification. Then BE and CB junction is forward bias. Base to emitter and collector to base junction is forward bias. Small changes in like a VCB will cause big difference to IC. Yes, that's true. And the allocation for this region is to the left of VCB is equal to 0, as we have seen. Then we can see about the cutoff region. Then in case of saturation region, we can use transistor as a switch. For switching purpose, we can use the transistor. Then again, this cutoff region below the line of IE is equal to 0 ampere, as we know. So BE and CB is reverse bias. No current flows at collector, only leakage current would be there. And that is why we can get this kind of the region is here. The curve's output characteristics clearly indicates that a first approximation to the relationship between IE and IC in the active region is given by IC is approximately equal to IE. So once a transistor is in the on state, the base emitter voltage will be assumed to be VB is equal to 0.7 volt. So that we are assuming. And then in the DC mode, the level of IC and IE due to the majority carrier carriers are related by a quantity called the alpha. Now alpha is also here current gain. Alpha is what? Alpha is the current gain for the common base configuration, and the value of alpha is always less than 1. So that you can see here typically it is 0.9. So that is why if we want to amplify the voltage, then we can use common base configuration as a voltage amplifier. So alpha is equal to, you can see, IC upon IE. So it's a simply collector current upon emitter current, and IC is equal to alpha IE plus ICBO, and it can then be summarized to IC is equal to alpha IE. So ignore ICBO due to small value. And for AC situations where the point of operation moves on the characteristics curve, and alpha or the AC alpha defined as delta change in collector current with the change in emitter current, and the alpha is simply like a current gain alpha, a common base current gain factor that shows the efficiency by calculating the current percent from current flow from emitter to collector, and the value of alpha is typically from 0.9. So it is less than 1 always. So here you can see proper biasing of the CB configuration. In active region, by approximation, simply IC is approximately equal to IE. Already I have mentioned, because IB is approximately equal to some microampere, not the 0 microampere. So in that way, we can see, yeah, transistor as an amplifier. So how it can be used for the process of amplification of the signal. so that we can see here how the biasing is there and how do we move ahead. Now, simply here you can see, as we know, we are using various applications like a speaker, where we know if we are having huge number of audience, then we use the speaker or the loudspeaker. And again, as we know, the function as we are using the mic, and we are just mic is basically transducer, and then it will passes signal to the amplifier, and amplifier is made of the transistor. And we can see here we can see very good animation how low can be bigger with respect to the initial one. So common emitter configuration, it is called the common emitter configuration since emitter is common or reference to both input and output terminals. So that is why it is called a common emitter. Now, emitter is usually the terminal closest to or at ground, closest to or at ground potential. So, almost amplified design is using connection of CE due to the high gain for current and high gain for current and voltage. And two set of characteristics are necessary to describe the behavior for CE: input base terminal and output collect terminal parameters. Now here you can see, like again, I have mentioned earlier, IE is equal to IC plus IB. So it's the most important equation, and how biasing for the common emitter configuration is here. And in case of common emitter configuration, the current gain is denoted as the beta. Okay, beta is equal to IC upon IB, IC upon IB. So this is what the simple input characteristics for the common emitter also. It is just like a common base. Okay, similar for common collector also. And if we see the output characteristics here, you can see how it is differ from the earlier figure. And here simply it begin from the positive, it is not from the negative. That was only possible for the common base configuration. And here simply you can see here how the characteristics is. And here also we are having the similar region. This is the active region, this is the cutoff region, and this is the saturation region. And again, the similar kind of application of the transistor is there. And but simply if we see this particular table, then we can compare how transistor can operate in active region. So base to emitter junction is forward bias, and collector to base junction is reverse bias, and can be employed for voltage, current, and power amplification. So this can be used for the voltage, current, and power amplification. This is the most important application of these configurations. Then in saturation region, base to emitter and collector to base junction is forward bias. Thus the values of IB and IC is too big. The values of VCC is so small. So suitable region when the transistor as a logic switch, saturation region, and not and avoid this region when the transistor as an amplifier. Then cutoff region below the IB is equal to 0 microampere is to be avoided if an undistorted output signal is required. So base to emitter junction and collector to base junction is reverse bias. So IB is equal to 0. IC is not equal to 0 during this condition. So this is what the common emitter operations. And here we can calculate the beta or the amplification factor, and the value of beta is more than 100 always. So ratio of the DC collector current IC to the DC base current. Okay, so beta, so which is a DC current gain, where IC and IB are determined at a particular operating point. Again, the quiescent point is there that we can draw. If we draw the DC load line and the AC load line on a output characteristics of the transistor, then we can get a quiescent point. And quiescent point we can consider the operating point of the transistor. Again, remember these two words for MCQ type of the questions, and some values which is written on this particular slides. So it's defined by following equation: 30 is less than beta, DC is less than 300. Okay, it's like you can show on data sheet this beta DC. Again, there are some hybrid parameters. So H is derived from AC hybrid equivalent circuits. So that is again another lecture that we can devote for that. Then simply for AC conditions and AC beta has been defined as the changes of collector current compared to the changes of base current, where IC and IB are determined at operating point. Okay, so in that way, we can have the like a common emitter biasing also, and in that we can have some calculations for that. So another thing is you can see from output characteristics of the common emitter configurations, we can find the beta AC and beta DC with an operating point at IB is equal to 25 microampere and VC is kept at 7.5 volt. So let us see how do we calculate these values like a beta AC and a beta like a beta DC. So let us see that beta AC is equal to delta IC upon delta IB for VC is equal to constant. So simply we can have this IC2 minus IC1 upon IB2 minus IB1. Simply is equal to 3.2 like a milliampere minus 2.2 milliampere upon 13 microampere minus 20 microampere. And we can solve this by just multiplying by 10 to the power minus 6 and by 10 to the power minus 3. So we can get our answer in ampere but basically both units are in ampere, so that will get cancelled, and that is why we can get the parameter only 100, and that 100 can be considered as a current gain. So this is what the current gain. And here also the beta DC you can see 2.7 milliampere upon 20 microampere. Again we can convert it to same unit, so we can get it 108. So in that way, both the gain is approximately similar, but it has a difference. But depending upon the applications, we can use the gain. Now, here just simply we need to understand from this particular graph of output characteristics. So as we know here, we have drawn the we have drawn simply, we can see two two lines. Simply, what we can say, the DC load line and the AC load line. Here you can see. So if we draw appropriately, just delta IC, you can see IC2 and IC1. Here, these are the 2 points in a active region, and here the point comes out to be, and then that point, then you can see that point is called as a quiescent point, or a quiescent point, or we call as a operating point. And in that way, we can have the calculation for that operating point also. Here we can use some cases, and with the help of these cases, we can solve this. Case 1, I is equal to IC plus IB. So yes, we can have the equivalent circuit IC is equal to beta IB, that we can put into 1. So we can get IE is equal to beta plus 1 IB. So here alpha is known to us, beta is known to us. From that, IE and IB we have calculated. And from that, we can have the relationship. Alpha is equal to beta upon beta plus 1, and beta is equal to alpha upon 1 minus alpha. So these are the two relationship in between the common emitter and the common base configurations. So like last configuration, we can discuss, and then we can stop, like a common collector configuration. So common collector, or again, as a like for competitive examination, again you must remember here. So here this common collector configuration is called as the emitter follower. It is also called as the emitter follower. So it is called the common emitter configuration since both the signal source and the load share the collector terminal as common connection point. The output voltage is obtained at emitter terminal. The input characteristics or common collector configuration is similar with common emitter configurations. So these are some of the common things. That is why just I am moving fast as we have 10 minutes. So this like a common collector circuit configuration. Common collector circuit configuration is provided with the load resistor connected from emitter to ground, and it is used primarily for, yes, you must remember this is the most important. Rest of the things are similar. So this is used for the impedance matching. Okay, impedance, again you may be knowing the impedance. Impedance is the total resistance offered by the circuit, and we need to match the impedance when we want to connect the two circuit. And in that case, the common collector configuration can be used, or as a buffer, basically that can be used as a buffer. So purpose, since it has a high input impedance and low output impedance, and this is the ideal characteristics of any of the circuitaries, and that is why this type of the configuration is used. Got it? So you must remember the application of common collector is impedance matching or as a buffer, because here we are calculating the gamma. Gamma is the current gain, and which is equal to 1, approximately equal to 1. And that is why this is more suitable configuration as a impedance matching or as a buffer. So this is the typical and one of the best application of the common collector configurations. Again here we can make collector common to emitter and base, and accordingly we can show the diagram. So here you can see how it is collector is common and how the circuitry is made. So here we have given potential to base to collector, and here you can see the emitter to collector. So in that way, we can have the common collector configuration. And here you can see for the common collector configuration, the output characteristics are a plot of IE versus BC for a range of values of IB. So here you can see Again, the similar kind of the characteristics we can have for the common collector configurations also. But here we can see some of the limits of operation to this. So many BJT transistor use an amplifier. Thus, it is important to notice the limits of operations. Okay, so how and means what to do and what not to do. So at least three maximum values is mentioned in data sheet. There are maximum power dissipation at collector like PC max or PD, maximum collector emitter voltage, sometimes named as VBR, and maximum collector current. So these parameters must be known or used while using the any of the transistors. So here you can see how it is. So simply here we can see the maximum power dissipation, which is shown here, and these are the some of the steps. Yes, we can have. So like derating, PD max, and some of the examples also we can solve. So here just the here just we can see some of the lines over here. And then this is a transistor specification sheet. Simply, these are for your information. These are some of the like transistors, how it is looking, how it looks in reality. So you can see we are having this type of the transistor in our laboratory. We are having this type of the transistor. These are the types of the power transistor and other transistor with their numbers also, and how to test that transistor so that you may be knowing. So we can test the transistor by this ways. So here just I want to stop for today's session. So thank you, Bharti, for giving me an opportunity to discuss about this very much important topic. And really it's a basic of this particular topic, but most important for the students of like a NET and SET examination, as well as the PG like a PG students, because these students are going to become the teacher. So thank you once again, thank you. So Dr. Nilesh Ugemuge is signing off. Thank you.